Hello guys, Sir DV is here to continue our discussion on stress analysis. So last time we talked about some properties of stress quadrics. Today we will be going directly to the solution on how to determine the principal stresses uh, from a given stress tensor, no? Knowing for a fact that the Cauchy stress tensor is defined on the basis of the stress tensor and the normal vector, the unit normal vector, okay? So we now seek a solution or orientation wherein this stress vector formula will have the same, okay, uh, stress vector involved, but for a different uh, value of your stress tensor defined on the basis of what you call a principal stress, lambda. So lambda here is actually uh, the principal stress upon which your stress tensor is converted to a pure normal stress behavior. Okay, so if I have a principal stress, a lambda, okay, so I use a different Greek letter to not confuse us later, no, on the variable. So lambda now is simply a pure state of normal stress, okay, wherein all the off-diagonal elements become zero. So we will try to find an orientation or a set of axes upon which your Cauchy stress vector will be the same. No? The only difference is that your uh, set of axes defined on the basis of the unit normal vector nj is different from the original uh, set of uh, direction vectors. Okay, so for this, we now uh, formulate by substituting your nj or converting your nj into an ni using the Kronecker delta Shor substitution operator. So take note that if we make use of contraction here, so substitution means we do not change the quantities, the values, but rather only change, no, the subscript so that it would fit, no, the intended purpose in terms of indicial notation. So this is now Ni delta Ij. Nj will collapse into an Ni. And if we substitute, okay, the value of your Cauchy stress vector sigma I in terms of sigma ji nj, and taking note that we now seek a solution for lambda in the terms of a lambda delta ij nj, okay, so this came from this ni here. uh, so this is simply, sorry class, this is sigma lambda Ni. Okay, so this is an Ni. We will yield now to these two equations, upon which, by simply make use of factoring, collecting similar terms nj, we now created a value inside the parentheses equivalent to sigma ji minus lambda delta ij, known as an eigenvalue problem. Okay, so this is now an eigenvalue problem upon which the term inside the parentheses uh, has to give you a non-trivial solution uh, if the determinant of such value is equivalent to 0. So vanish means the determinant must be equivalent to 0, or else there will not exist any solution for lambda and nj aside from, of course, having it to be 0. So the checking of the determinant of this value inside the parentheses will give us now a procedure on how to determine the eigenvalues for lambda. No? So lambda now will be obtained by simply uh, making use of a determinant procedure or operator in this regard. So if I do it, expanding and collecting the terms, we get a cubic equation in this form. Okay, so the expansion is quite very involved. Okay, so we will be yielding this type of equation where the cubic, the square, and the first degree equation or the linear equation will constitute uh, coefficients including the constant, which has uh, this value happen to be a simplification of a determinant. So this value here is actually a determinant procedure. Okay, while this and this are known to be your first invariant, second invariant, and the last is the third invariant. Okay, so I just made a change in the sign here. So I make it minus plus, plus minus, minus plus, and then a plus minus, so that the terms inside the parentheses will now be set into these three values. Okay, and these three values here, which are called the invariants, uses the initial form of the trace of a stress tensor, 1/2 the difference between sigma I sigma jj minus sigma ij sigma ji, and the third is simply the determinant of the original. Okay, so we are referring here to the original stress tensor given or cited in the problem. So to give you a good understanding on this, I have now here example 2.9, wherein we are asked to find the principal stress using the method of invariance. So at a point in a continuum, the components of the stress tensor are given. Okay, again, this must always be symmetric. So if I give you a tensor which is not symmetric, then there's something wrong with the problem. Okay, so maybe it's a typo error, or maybe a special condition is set on the problem, not to qualify why symmetry was not satisfied. So using stress invariance and using MathCAD as my tool to solve for the values, okay, directly. So I just have here the trace function, simply the summation of I 1 to 3 of sigma I. So I get 6, okay. And for I2, I just take the summation I1 to 3, J1 to 3 of 1 half this sigma I, sigma JJ minus sigma IJ, sigma JI. And this is equal to -4, and simply the determinant of the stress tensor given here above is simply 24 or negative 24. So for the long method, you can use manual calculation. So for the sigma I, which is a summation of the diagonals, I just add 1 plus 1 plus 4. And for the summation of 1 half sigma I, sigma JJ minus sigma IJ, sigma IJ, I just multiply, no? The values of the diagonal tensors here is the sigma i's and sigma jj's are actually the diagonal values, while here I have the off diagonal values. Okay, of course I also have a diagonal value here, but since I did not use the 1 half here, because on the diagonal values you opt to repeat the process twice, okay? So here, this is done twice. And also here, this is done twice, including the diagonal values. But since this is a 1 half, there's a 1 half, okay, coefficient there, these two here and 2 here will simply be equal to 1. That's why at the end of the day, you ought to only use one cycle of each diagonal multiplication. So if you have a permutation of 3 i's and 3 j's, okay, so this is a 3 times 2, 6 set of multiplication will be placed here. Okay, so also here 6, but I only use 3 multiplication on the uh, off diagonal elements, and since they are symmetric, I only need to square them, okay, and therefore not dividing it by 1 half will simply yield to an exact value of -4, which is this one here. Okay, so I'd like you to figure it out by your own so that you will appreciate what I have done here. You cannot appreciate if you will not do it, no, by means of expanding. And of course, the determinant is simply a an exercise of multiplication of diagonal rows and columns. Sorry, rows downward and upward. So all of these values here are positive downwards, okay, and all of these values here are negative because they are downwards, okay, so negative, negative, and negative. So you get again a value of -24, which is the same with my MathCAD determinant command, okay. And then using now my formula for the cubic equation, this is my equation. My I here, sorry class, this is cube, sorry, this is square. So this is my I1, this is my I2, and this is my I3, okay. So remember that this is minus plus minus. So if I get the positive minus plus minus minus, and this is a minus minus, it's plus, okay. So I get now this as my cubic equation, and by factoring, I can say that these are my factors, 6, 2, and negative 2, for which my principal stress are obtained in terms of sigma 1, sigma 2, and sigma 3. Okay, so the lambdas here will constitute the values of your principal stresses. Normally, your sigma 1 is the highest, bigger than sigma 2, and sigma 2 is bigger than sigma 3. So this is a normal way of how to indicate your principal stresses, but if you want them to be the other way around, there's no problem with it. Okay, so that's it for the solution to stress analysis by the determination of your principal stresses. So next lecture will be how to get the principal directions or the principal axis uh, by using analytical calculation, and then perhaps we will relate it to the use of more spherical representation for both two-dimensional and three-dimensional cases. So thank you very much for listening. I'll see you on the next video.